All right, let's dive right in. In this explainer, we are going to deconstruct the absolute core of Cisco's application-centric infrastructure, or ACI. We're going to break down the logical building blocks, how ACI organizes a network from that high-level policy all the way down to the nitty-gritty of Layer 2 and Layer 3 forwarding. So, here's our game plan. We'll start with the big picture, ACI's overall logical model. From there, we'll zoom in on each key piece of the puzzle. We'll start with tenants, then drop down into VRFs for routing, and then bridge domains for switching. By the end, you'll see exactly how these pieces lock together to create a much smarter, policy-driven network. You know, to really get ACI, you have to understand its core philosophy first. And it really is a fundamental shift in thinking. We're moving away from the old-school method of configuring individual boxes and worrying about point-to-point connectivity. Instead, we're moving towards defining the intent of your network through a centralized policy. And this diagram right here, this is that new way of thinking, visually. This is the ACI policy model, and it's all about hierarchy. At the very top, you've got the tenant. Just think of that as the main container for, say, a business unit or a customer. Inside the tenant, you have one or more VRFs. That's where all your Layer 3 routing happens, creating these nice separate IP address spaces. Below that, you'll find bridge domains, which are like a supercharged version of a VLAN for all your Layer 2 connectivity. And finally, at the bottom, your actual devices, your servers, your VMs, are grouped into what we call endpoint groups, or EPGs. And that's how policy gets applied. Understanding this top-down structure, that's the key to everything in ACI. Okay, so let's start at the very top of that pyramid with the tenant. This is the highest level building block you can have. It's really the foundational container for pretty much all networking and security policies inside the ACI fabric. So the official definition is that a tenant is a logical container for application policies that lets an admin exercise domain-based access control. Okay, that sounds a little academic, right? A much simpler way to think about it is like putting a big digital fence around an entire department or maybe a specific customer's environment. It holds all the networking and security rules for just that one entity. And the real power here is just how flexible this concept is. A tenant could be a single customer in a big data center, or it could be a business unit like marketing, or it could just be a logical group of applications. But the most important thing to remember is that it provides a completely separate, isolated space. By default, tenants are completely walled off. Traffic can't pass between them. It's a foundational security principle baked right in. Of course, you can poke holes in those walls to share services when you need to, but the default is total isolation. And this visual really drives that concept of isolation home. On one single physical ACI fabric, you can host multiple, totally distinct tenants. Each one is its own little self-contained world of policy, with its own VRFs and network constructs, completely unaware that the others even exist. This is what lets a service provider host multiple customers securely, or lets a big company cleanly separate different parts of the business on the same hardware without any fear of overlap. Now, when you first boot up an ACI fabric, it doesn't start from a completely blank slate. It comes with 3 tenants already configured for you. First, you have the common tenant. This one's special. It's designed specifically to host shared services. Think DNS, DHCP, Active Directory, things that a bunch of your other tenants will need to talk to. Then there's infra. This is purely for the internal plumbing of the fabric itself, and you don't ever put user traffic in there. And finally, you have MGMT, which, as the name implies, is for managing the fabric itself, both in-band and out-of-band. Okay, let's drill down one level from the tenant and get into the Layer 3 context. We're talking about the virtual routing and forwarding instance, or as we all know it, a VRF. This is where we carve out our private IP address spaces and define all our routing policies. Now, for anyone who's been in networking for a while, a VRF in ACI serves the exact same purpose you're used to. It's basically a virtual router. It has its own completely separate routing table. That means you can have the same IP address space, say 10.1.1.0/24, in 2 different VRFs, and they won't conflict at all. It is the primary tool for creating distinct Layer 3 worlds inside of a tenant. So just remember, each VRF is its own little Layer 3 universe. A single tenant can have many VRFs if you need to separate things out. But here's one of the most powerful, and I mean critical, settings on a VRF. It's called Policy Control Enforcement. By default, this is set to Enforced. That means you're in a zero-trust model. Nothing talks to anything else unless you explicitly create a policy, a contract, to allow it. If you set it to Unenforced, you're basically saying, if you can route, you can talk. It's a huge security decision you have to make right at the VRF level. Okay, let's make this practical. Look at this design scenario. On the left, we've got a really common but pretty inefficient design.
To keep sales and finance separate, the admin created two separate tenants. Now, because they're in different tenants with different VRFs, getting them to talk to some shared service requires some pretty complex and messy configurations we call VRF route leaking. It's often brittle, and it just doesn't scale well.
Now, contrast that with the ACI native design on the right. See how much cleaner that is? Instead of two tenants, we put both departments into a single tenant production with one shared VRF. The logical separation doesn't happen at the routing layer anymore. We push that down to the application profile and EPG level, where we can apply policy. This design is so much more elegant, it actually matches what the business needs, and it completely gets rid of that messy, complex route leaking we saw before. All right, let's keep moving down the hierarchy. We've covered the Layer 3 context with VRFs, so now we got to talk about Layer 2. And this brings us to ACI's mechanism for L2 forwarding, the bridge domain, or BD. A bridge domain is, for all intents and purposes, ACI's modern answer to the VLAN. It's the Layer 2 forwarding construct, your broadcast domain, that lives inside a single VRF. But it does more than a plain old VLAN, and this is crucial. A bridge domain is also where you define the IP subnets that will act as the default gateways for all your connected devices. And this right here is where you see what a massive leap forward bridge domains are. ACI solves some classic networking headaches. First, that 4094 VLAN limit, it's basically gone. VLAN IDs are only locally significant on a switch, so you can reuse them all over the fabric. Second, and this is a game changer, instead of having a single gateway on a core switch, the BD gives you a pervasive anycast gateway. That means the gateway IP exists on every single leaf switch at the same time. This optimizes traffic and makes moving VMs a breeze. And third, ACI can use its spine proxy feature to figure out where endpoints are, instead of just flooding traffic everywhere. That saves a ton of bandwidth. So, to sum it all up, a bridge domain is your L2 broadcast domain. It has to be linked to one and only one VRF. It can have multiple subnets inside of it, and each one of those acts as that incredibly powerful, pervasive gateway. And again, that gateway isn't stuck on some central device. It's active and available on any leaf switch that needs it, making the whole network way more efficient. And this diagram really puts it all into focus. See how the bridge domain lives right inside the VRF? This particular BD has two subnets configured in it. Then the endpoint groups are containers for servers and VMs. They attach to this bridge domain to get their Layer 2 connectivity. And when an endpoint in one of those EPGs needs to get to its gateway, it uses one of the subnets to find right here in the BD. Simple as that. So let's tie this all together. What this new model really does is it allows for a totally different way of approaching network architecture. We are moving away from that tedious, error-prone world of configuring devices one by one and into a centralized, policy-driven model that's all about describing your intent. And here we are, back in our master blueprint. Hopefully, this logical hierarchy is crystal clear now. Policy always flows from the top down. It starts with the tenant, which gives you that high-level isolation. Inside that tenant, your VRFs define the Layer 3 routing domains, and within those VRFs, the bridge domains create the Layer 2 broadcast domains and provide those amazing pervasive gateways for your endpoint groups. It's a clean, logical, top-down flow. And at the end of the day, what this all adds up to is a network that's actually built for the modern era. The ACI logical model, built from tenants, VRFs, and bridge domains, is designed from the ground up to create a scalable, automated, and policy-driven infrastructure. It's a network that's built to directly serve the needs of applications instead of forcing applications to work around the limitations of the network. And that leaves us with one final thought to chew on. When your job shifts from defining VLANs and IP routes to defining application intent and security policy, how does that fundamentally change the role and, maybe more importantly, the value of a network engineer?